Okay, so let's get started. So welcome back. What we will do today is continue the discussion from last time, where I gave an introduction to distributed systems. Today's is also an introductory lecture, but a more in-depth. Okay, so let's get started. So welcome back. So today's is also an introduction, but it's going to be a more deep dive into distributed systems architectures. Okay, so what we'll do is there will be three modules. We'll talk about architectural styles, client-server architectures, and then decentralized architectures, peer-to-peer architectures, and so on. Okay, so first, let's talk about very high-level architectural styles that you see in distributed systems applications. We'll talk about layered architectures, object-oriented, data-centric, event-based, and resource-based. Okay, so let's take a look at them one at a time. So let's start with layered design. Okay? If you have now ever taken a class in computer networking, the layered architecture should be familiar to you because protocol stacks use a layered organization. Okay? In the layered organization, your system is partitioned into layers. Okay? Layers are stacked. Each layer can communicate with the layer above it and the layer below it, but not with other layers. Okay? Layer I can interact with layer I plus 1 and I minus 1. Okay? That's how a protocol stack works. Okay? But that's also how many distributed systems applications are written. Okay? Specifically, one example of a layered architecture is a multi-tiered web application. Okay? So I presume you all know what a web application is. Something that you just connect with the browser and you have a server which is running the application and you interact with it. Okay? Now it so happens that the architecture of these applications is not one monolith. It's not one single thing, but it's a distributed application even at the server end. And that architecture involves multiple components called tiers. Okay? Tiers actually are the same as layers in this case. Okay? So that architecture is going to follow a very similar picture that's shown here. I'm going to just draw a small figure for you to explain this. So you can take a web application. Okay. So this would be requests come here. Okay. This is tier 1, this is tier 2, this is tier 3. So tier 1 will perform some request processing. Okay. And then it will hand off the request to the next tier. That next tier will perform more request processing and hand this off to the third tier. Okay. In this case, there are only 3 tiers, but you can have more in an architecture like this. But once you hit the final tier, responses are going to flow backwards. Okay. So the response from tier 3 will come to tier 2. It will take that response and process it and construct another response. And it will come back to tier 1. And then a response is sent to the client. Okay. That's how web applications are built. Okay. Simple web applications. There are many other architectures. So typically in this architecture, this tier 1 will be your HTTP server. Okay. That's your web server that's receiving HTTP requests. Okay. Tier 2 could be the application logic. So this is written in Java or Python or any of your programming languages. So this is the application tier. Okay. And tier 3 usually the database tier. That's where data is stored by the application. Okay. So this is called the data tier or the database tier. Okay. So you can see that this is actually a layered architecture because each tier can only communicate. In this case, there are only 3, but each tier only talks to the tier before or after it. Okay. So that's one organization. The other organization that's also common is object-oriented architecture. Okay. So all of you are familiar with programming languages like Java that use object-oriented programming. Okay. When you write an application, you have objects, your classes that get instantiated as objects. Objects encapsulate data in code. Okay. You can write a distributed application in a similar fashion, okay, where your application consists of a set of objects. It just so happens that these objects reside on different machines. Okay. These objects are processes that are running on more than one machine. In a Java application, all the objects are in one process running on one machine, a typical Java application. Okay. In this case, you'll have multiple processes running on multiple machines of your distributed application, and each of them may have some subset of objects, and these objects communicate with each other over a network. Okay. So this is called an object-based architecture. Okay. This uses object-oriented principles. Now, it so happens that even if you don't use object-oriented approaches to building application, this picture is representative of how many distributed applications are built. And you can see that this is a generalization of a tiered or a layered architecture. Okay. In a layered architecture, you had a restriction where the application could only, or the tier rather, would only communicate with two other tiers, the one before or one after it. This removes that restriction. Any component here can communicate with any other component through well-defined interfaces. Okay. So the multi-tiered architecture that we saw, okay, has evolved into a more general architecture, and there are applications that are written as small components called microservices. Each component is a microservice. Okay? And these microservices can communicate with one another to implement the application functionality. Okay? So microservices architectures also looks like this. They don't necessarily follow a strict layering or a tiered approach. Is that clear? Okay. The next one up is event-based architecture. So you can go there and get a chair from the conference room. Okay. So the event-based architecture, what you have are components that communicate with one another through what is called an event bus. Okay. So an event bus is essentially a communication bus that allows these components to talk to one another. Okay. Now, what is different between this and the other architectures we've seen in the past two slides? So here we use a paradigm called a publish-subscribe paradigm, or called a pub-sub paradigm. Okay. So what happens in this case is components can publish data, or they can publish events. Okay. Those events actually are communicated from the event bus to other components that are subscribed to some data. Okay. So you can say subscribe to all weather events whenever there's an update to the temperature in Amherst. Okay. This could be a component that's trying to subscribe to all weather events about Amherst. Okay, there may be another component, which is the weather server, that is publishing updates to all kinds of towns. Okay, and whenever one is published for Amherst, that event is going to get sent to the subscriber for that types of event. Okay, but other events are filtered out. Okay, so this is called a publish-subscribe paradigm, where consumers subscribe to types of events, and events are delivered by the event bus whenever components publish them. So it looks similar, but the way you communicate is different from the other two architectures, where you make requests and get replies. Okay. Yes, question in the back.
Is the event bus centralized, or is that also distributed?
Okay. Question is the event bus centralized, or is that also a distributed system? That's a very nice, good observation. I didn't explain what the event bus was. So the answer is it depends on the system. Okay. There will be large applications where the event bus is itself a set of machines, is distributed. Okay. But in other applications, the event bus could be one small, shouldn't say small, one centralized entity that's just receiving published events and then delivering them to others. Okay. So it will depend on the size of the application. But in the general case, the event bus itself is a distributed entity. Yeah. Any other questions here? Yes.
So components connected to this event bus are like a distributed in the sense like event bus is a network for components.
Okay. Question is, are the components connected to the event bus distributed? Is the event bus acting like a network? So event bus is the mechanism through which components communicate. The components are essentially applications or processes that are running on different machines. They communicate with one another through the event bus. Okay, it's a logical abstraction, but at the end of the day, it's going to be a machine or a set of machines that receive events and then deliver events. Okay. All right. Next up is a different architecture, which you presumably have not seen. It's called a blackboard architecture or a shared data space architecture. Okay, also sometimes called a bulletin board architecture. Okay, the reason it's called that is you can essentially make an analogy to what is you see in a bulletin board. Okay, so if you have seen a typical bulletin board, you'll see that somebody has come and posted a notice on that bulletin. Okay, the notice is not addressed to anyone specific. It's just something of general interest. Okay, so you can come and look at the bulletin board, see if there is something that's interesting to you. Perhaps somebody is selling some furniture. Okay, you're looking for a new sofa or used sofa, and it catches your interest. So then you can just essentially take that information down and contact that person. Okay, that's how bulletin boards work. You post notices, and people then look at them and basically gather an item of interest. So this is a similar concept where components are going to publish events or notices to this shared data space, which in this case is a bulletin board. And then later on, other components can come and query that bulletin board, saying, is there a note with this attribute? Is someone selling furniture? Someone selling a car? Is there a note that says there is a car for sale that someone has posted? Okay, so then you basically go get any information that actually matches your query, and then you can then process that information. Okay, so it is a very loosely coupled system in that when you publish data to the bulletin board, it's addressed to no one in particular. Okay, unlike a web server and a web browser, when you send a request, you're sending a request to a URL, it goes to a specific web server, it's addressed to the web server. Okay, in this case, when you say, I have some items for sale, it's just addressed to the general public, not to a specific entity. It's the same thing in this case. Okay, yes, question.
Can there be a component that publishes to the data space without receiving something from the data space?
Okay, question is, can you publish a component without receiving something, right? So it can be the case. You can just publish items of general interest, not have to receive a response from the data space. An example is you can have services that you advertise. Okay, you can say, I am a printer and I am available at this IP address. You just put that in the data space. Now somebody wants to print, they can go to the data space, say, is there a printer? And then you essentially get the IP address. Then you send a print job. That's not coming from the data space. That's directly coming from the client. Okay, there's a question somewhere. Yes. Okay, what if multiple components access this at the same time? So the data space has to arbitrate that. So first of all, the data space itself doesn't do any synchronization or anything like that. It's not that the notice is meant for only one person. Maybe you have 10 items for sale, right? So then 10 people can look at it at the same time. So it doesn't mean that once you publish something, only one other component can access it. You can have any number of components that can access that piece of data. Yes, question.
In a simple web application, if you have a database at the last layer, would that be considered as a shared data space where multiple computer machines are querying the database or storing data?
The question is, if in a web application, if your database as your final or the last tier, would that be considered as a data space? So in the web application, databases are not considered data spaces because they are traditional databases. Okay. In this case, the communication is decoupled in space and time. Okay. You can publish some item to your data space. Nobody may be interested in it. That will never get consumed. Okay. You're publishing something saying, I'm selling some exotic furniture that nobody might be interested, right? So it never gets consumed. Okay. Or you might make a query and come empty-handed, but those queries can come at a later time. So this is more loosely coupled in databases where you make a query, you get a response to your query. That's not the case necessarily here. Okay. Yes, components are going to query for items of interest, but the what has been posted may have been done much earlier in time. It's not specifically addressed to someone and so on. Okay. But it's not, this is implemented using a database internally, but the data space does not give a database abstraction at the end of the day. Okay, yes, question.
Can you give some differences between this and object architecture?
Okay, can you explain differences between shared data spaces and a publish subscribe architecture? In a publish subscribe architecture, you have to subscribe to events ahead of time. whenever an event is published, the subscription lists of all clients are matched and only matching ones are sent to those subscribers. Okay. In this case, you don't need to subscribe to anything. You publish events, some component application can come at a later time and query. And if there's a match, you just get that. So it's not like a subscription where as soon as an item is published, it's delivered to all the subscribers. Okay. So in that case, there's a temporal difference in how data gets delivered.
Can the
Yes.
components modify the data or like only the publisher can modify the data?
Okay. The question is, can the components modify the data or the publishers can modify the data? That actually depends on the application. There are components that can modify or even remove the item, okay, from the data space. Others can just read it and not remove it. So there are different models that data spaces will support. Okay? There's no one way to do it. It's just an abstract answer. We'll come to actual implementations later. Okay. No question there.
So would there be a scenario where something is published and it's not immediately found? What would happen?
Okay. Question: is there a scenario where you can publish something but it's not needed by someone else? What would happen? So when you publish an item to your data space, there's no guarantee that anyone will ever need that information or how many users will need that information. You're just publishing a note or a notice, right? So who's interested, you don't know. When they will be interested also, you may know. It may be one day, 1 hour, some period of time, or never, right? So it's just, that's why it's loosely coupled. You don't know whether you have whatever you're publishing will ever be consumed by someone. Okay, yes.
Do the components not communicate with each other apart from through the data space?
Okay. Question: do the components not communicate with each other apart from the data space? So data space is primarily the way they are communicating in this case. Okay? Once you have some information, they can enter through some separate communication channel, but that's no longer part of the data space application. Okay. So I mentioned the printer example, right? So you can look for a printer using this model, but once you found it, you can directly communicate with the printer. But that's not, that printing is not part of the data space. This was just discovery of a printer. Okay, yes.
So what if the data is completely fills up and you just keep publishing, there's no one to take it? So
Okay, so question is, what if the data space you keep publishing, nobody accepts it? I think it's not a very useful application in that case. And nothing actually is happening.
Publishing, how will they make sure that publishing is still taking place? Because maybe I'm publishing, the application is publishing in the end, it's an important information, but because it's filled up, my information, what will happen to that?
Okay, so maybe you're asking a different question. So you're asking, can the data space, does it have a capacity limit? Can it fill up? So we don't assume in this abstract case that there's any limit. Assume you can publish whatever you want. Okay. But yes, technically there will be a limit. But right now we are talking concept, we're not talking actual systems. Okay. Yes.
So, in the previous system where there was an event bus, so essentially the event bus does not have any data to hold, right? That is just the way they are communicating. So it's just the system to deliver whatever is being published, right?
Yeah. So question, yes, keep going.
Yeah. So one component is publishing, the other needs it. So this is just a delivery thing, and it does not hold any data within itself, right?
Okay. So the question is, in the event bus architecture, can the event bus actually store information, or is it just merely a communication channel where events are published and they're immediately delivered and then that's done? Then there's no sign of that event anymore. So technically, you can actually have different types of event buses. There will be some buffering in the event bus. So there's limited amount of storage. Unlike in this case, this could be assumed to be a database on disk. So information is held for a long period of time. Okay, by default, when you have event channels or event buses, they have memory buffering. So you can hold it and then deliver, but you don't have long-term storage. Okay, but there's another system which is called message queuing. Okay, that also uses PubSub. We'll get to message queuing later. When you have MQS systems, message queuing systems, you will have actually long-term storage. Okay, so there's a variant of an event bus model that can actually store events for long periods of time on disk. But for now, let's assume that is not the case. Okay, it is merely a communication channel. But every variant you can think of, there is something there. Okay. All right. Okay. So with that, let's talk now about a different architecture altogether. So this is called a resource-oriented architecture, ROA. Okay. It's a very common architecture used in web services today. And the way it is used in web services is through what is called a REST-based interface, okay, or a REST-based service. And REST is a term that acronym that means representational state transfer. So what this essentially does is it assumes that all the entities in these applications are resources, okay, and resources have names, okay, and all of the communication between components of this application is going to occur through using these names to invoke resources. Okay, so everything is a resource. Okay? A piece of data is a resource, a function is a resource, whatever you can think of is actually a resource. And then you can use these names to invoke those resources, to invoke a function to access a piece of data and so on. Okay? So that's the basic idea. So essentially, all of these web services that you see today, I shouldn't say all, but many of them use this mechanism to expose their interface. So they are called RESTful web services because they use REST interfaces. Okay? And very soon you will implement one in the lab, so you understand this much better. Okay? But the basic idea of implementing a REST-based interface is first, you are going to use HTTP. Okay? So it's web-based. So you're going to use HTTP as the protocol for communication. And the names that I'm talking about are essentially URLs. Okay? But the URLs are not something that end in a .html and access an HTML file. The URLs actually invoke functions. They invoke pieces of data that's stored on other applications, as opposed to a standard URL, which could just get you an HTML file. Okay? So using the same concepts of HTTP, but you're using this for communication. You're using this to access resources, to invoke functions sitting on other machines and so on. Okay? So that's essentially the basic idea behind a resource-oriented architecture, where the application essentially is a collection of resources. These resources have names, and you communicate or interact by invoking these resources. Okay, and in the RESTful case, the resources are accessed using HTTP. Okay, so all the names are essentially, they look like URLs. So you'll say HTTP, some server name / stock price. Okay, so then you basically invoke some method to give you stock price, or you can say weather / Amherst, and then it'll give you the weather in Amherst. Okay, so that's essentially how you are going to invoke these services. Okay, very common way to build applications, okay, web applications in particular. Yeah. So now when you invoke these requests using URLs, the response comes to you not as a standard HTML page or anything like that. It comes as a JSON object. Okay, so essentially you'll again learn about how you can send back responses. So JSON objects are a common way to send back a response to any request you make to this service. Okay. So I'll leave it at that, and we'll come back to this a bit later. So there are two things we have discussed. We have object-oriented and resource-oriented. Excuse me. There's a third architecture, which is called a service-oriented architecture. Okay. So as the name service-oriented architecture indicates, your application is a set of services. Services expose some methods that you can use to invoke that service. Okay. This was a common way to build enterprise application in the pre-web world. Okay. So essentially, you wrote your distributed applications as services. They expose some interface, not an HTTP interface, just some other arbitrary interface, and the services communicated with one another through these interfaces. Okay, that was the old way. Now you can write this using an object-oriented architecture or a resource-oriented architecture. So that's basically the more modern way of writing distributed application. Doesn't mean that the service-oriented architecture is gone. If the service-oriented architecture exposes a RESTful interface, okay, you are essentially have a mix of both. You have a set of services that are exposing RESTful APIs that you communicate with one another. Okay, so you can still write service-oriented architecture using RESTful APIs or using objects. Okay, but these are more modern ways you can essentially implement your application. Okay, so let's look a little bit at the details here. So I'm not going to go through all of these concepts. Only thing I want to mention is service-oriented architecture. The way you did this is you essentially specified a protocol that the application uses to communicate with one another. It used a heavy-duty protocol compiler to essentially create the interfaces. Then you wrote the application in some language, C++ or Java or some other language of choice, and then you put it all together. Okay, so this was a somewhat heavyweight way of writing application. Okay, in RESTful applications, their interface is very straightforward. It's essentially a set of web URLs that you say this URL will invoke this resource. This resource is essentially going to invoke this method or essentially access this piece of data and so on. Okay, and then you just write a web application. Much simpler, okay, to implement. Okay? And in this case, you can use object-oriented languages to write this, but you can also use a similar technique to service-oriented architectures where you have an interface definition, then you have an interface definition compiler that's going to essentially create a interface for you, and then you write the implementation of that interface using your language of choice. Okay. So there are different ways to implement these, and you will get some sense of how to do this when you start doing the labs. Okay, so that will make you implement some simple web applications using these concepts. Okay. Yes, question.
So resource-oriented is like architecture filled with resources, and service-oriented is architecture filled with services. So like, isn't that the same thing, like services and resources, are they?
Okay, question is, in resource-oriented, the system has a set of resources. In service-oriented, there are a set of services. Are they not one and the same? Okay. It depends on how you think about this. So resources could be you're invoking a function which is code, or resource could be you're invoking request for data. Okay. In service-oriented architecture, you always invoke the service. The service might then request, retrieve data and send it back to you, but you can't directly ask for a data item. You are invoking the service. Okay. But one way to think about it is that services can be thought of as a collection of resources. Okay, and then use a RESTful API, and there is not much difference. The only difference is there is a specific way to implement this that you are not going to follow there. Okay? So there's a conceptual difference, there's an implementation difference. Conceptually, you can make them look similar, but implementation is a very different way of writing them. Yes, question.
What is meant by replace cacheable?
Okay. Question is, what is meant by a replies cacheable? So in most of these distributed applications, you can essentially have caches that take the responses to request and store them. Okay. Now, if another request comes, you can first look in the cache to see if someone else has made that same request and is the reply already in the cache. If so, you are going to essentially send the response without invoking the service. Okay. So now what is actually said here is typically in resource-oriented architecture, since it uses HTTP, okay, it is easier to cache replies because you can essentially say, here's an HTTP request, here's the response, you can use standard web caching and cache that reply. Okay, that is not the case in object-oriented. You can't just put a cache in front of a Java process. Okay, that kind of concept doesn't actually exist. Okay, so it's much harder to do this. So that's why it says typically replies are not cacheable because the architecture is not designed for that. HTTP applications, because HTTP itself, there's web caching, you can essentially integrate caches into that architecture much more easy. Okay, and RESTful applications are web applications. Okay.
For object-oriented and service-oriented, I mean, you can still implement it, but it's much harder to do.
Implement what? You're asking about caching?
Yeah.
So typically you would not put caching because there is no concept of integrating caching in that architecture by default. You'll have to do something else. Whereas in this case, it's much easier because web caching is a standard thing that you can do. Okay. If somebody had a question. Yes, go ahead.
How is the communication happening over network in object-oriented?
Okay. Question is, how is communication being done in object-oriented program architecture? So in this case, the objects are processes that reside on multiple machines. Okay, and then they basically communicate over a network. So you are going to call methods on the object just as you call methods on a Java object. Okay? It's just that the code of that object is on some other machine. So your invocation of that method has to go over a network. Okay? When we talk about remote method invocation in a class or two, we will see how that is done. This is RPCs, RMIs, they all use this concept. Okay. Any other questions? Okay, so done with module one. Okay, reminder that we have a no device policy, which is good because somebody has a device open right now. Okay, and there's a career fair in the engineering college, but open to all engineering students and computer science students on Feb 28th. So if you're looking for internships, jobs, make sure you go there. Okay. Next, you're going to now look at client server architectures in module 2. Module 3 will get to peer-to-peer architecture. Okay. So this architecture should be familiar to you because if you use the web browser, that's your client. The web browser talks to web server, that's a server. So that's the standard way of writing an application, a distributed application, where there are clients and there are servers. Clients send requests to servers. Servers process that request and responses. Okay, that's what is shown in that picture, where the top line, so the x-axis here is time. Okay, so it's showing that the client, the black solid means the execution. So client is executing, sends a request, request goes over the network to the server, server processes that request, client is blocked, that's why it's dotted. And then a reply comes back, client continues execution. Okay, this is the standard blocking client that is making a request of a server. You can do non-blocking as well, but we'll get to that later. Okay? So that's your client server architecture that is essentially used in many distributed applications. Okay? Now, one thing to realize is there's a lot more subtlety in the client server architecture in terms of what functionality are you going to put at the client and what functionality of the application are you going to put at the server. Okay, and we care about three different things at a minimum. Okay, where is the user interface? Is it at the client or the server? Likely at the client. Okay, where is the processing done? Okay, and then where is the data stored for the application? So that's essentially the user level, the processing and data level. So somewhat maps to the multi-tier thing I was talking about, the HTTP tier, the application tier, and the data tier, except that in this case, we will see that there are many more dimensions of flexibility. Okay, in the multi-tier, all of those three things were actually at the server. Okay. So to understand this a little more, let's take a simple example of a web search engine. Okay, so and we'll see what is put there. So in this case, the user interface is at the browser. Okay, that's the box, the search box that you have. Okay, you're just going to type a query and send it off. Okay. So the user interface tier is at the client. Okay. So now when the search query comes, it's essentially going to come to your search engine. It is a simplified search engine, a trivial one. Okay. So it's going to take your keywords and generate a query from that keyword. Okay. Then that query is going to go to some database that has already indexed web pages and is constructed a database of web pages, indexed content. Okay. Some response is going to be generated from that database. Okay, that response is going to get ordered by something called a ranking algorithm that's going to decide what is the relevance of each of the retrieved responses to the query that was made. So you are going to get the responses in some order, which is basically determined by the ranking algorithm. Then that ranked list is going to be sent to an HTML generator. The HTML generator will make a web page of this response, and then it will come back to the client. Okay, you don't need to understand search engines to understand this. All that I'm trying to say here is all the processing, okay, of that query is now actually, or the keywords that you sent are being done at the server. Okay, so the processing is all done at the server. The data level is clearly at the server. That entire database is at the server. Okay, so the top dotted line there is the boundary between the client and the server. The user interface is at the client, the processing and the data is at the server. Okay? That's a fairly common way to do things, but that's not always going to be the case. We'll see many different examples where the boundary between the client and the server can shift up or down. Okay, so essentially, you have now multi-tiered architecture at the server. I already mentioned that, so I'm not going to go into this again. Okay, so now let's look at some other alternatives. Okay, so this shows 5 different alternatives to where you are going to put the user interface, the processing, and the data. Okay, the dotted line that you're seeing is the boundary between the client and the server. Everything above the dotted line is at the client. Everything below the dotted line is at the server. Okay, so here is the first example where the user interface is split between the client and the server. Part of it is at the client, part of it is at the server. Okay, the application tier and the database tier are at the server. Okay, what's an example of this? Yes.
There's a technology called server-side rendering,
Yes,
where you take a React.js app and it actually renders on the server, sends you back JavaScript, but it is also interactive.
okay. So if you have JavaScript type applications, some of this is actually done at the server, some of this is done at the client. Okay, because the server is participating in the user interface aspects of it. Okay, processing and database all at the server. Okay, here's another example. User interface is at the client, the application and database at the server. Okay, yet another example is the application is split between the user interface, this part of the application here, part of the application on the server, database is at the server. Okay, you think of an example of this scenario.
Fall into this because there's some logic on the client on the app side as well.
Yes, but specific examples. Okay, mobile application. Anything on your phone that talks to a backend has this example, right? So you have a UI on your phone app. There's the part of that app that's actually running on the phone. Okay, and that app is actually talking to something at the backend, right? Maybe it's Facebook, maybe whatever it is, right? Main server, right? So that application has some part at the server, the data is at the server. Okay, that progression will continue. You can now put the entire application, okay, and the user interface on the client. Only the database is at the server. Okay, you can think of full-fledged application that might be running on your laptop or desktop, where they just talk to a database at the backend. Okay, the entire application is actually on the server, and you can even now move some of the database or data at the server. Maybe it's a cache. You don't have the whole database, but for if efficiency, you just cache part of the database at your client. Okay, so the whole spectrum of choices as to what you put on the client, what you put on the server, the web applications, there are mobile apps, there are full client-based apps, and they will all have different architectures. Okay. So in all cases, we still have distributed applications because there's a boundary, because there's a client, there's a server, and there's a boundary between the client and the server. So the application is split across multiple machines, at least 2, maybe more. Okay, any questions here?
So is the last one like a cache database? Like we have some of our information in cache and then it's.
Okay, the question is this last scenario where the database is split between the client and the server, is that a cached application, right? So it could be a cache where you have a database cache that is stored something, or it could even be that there is some part of the database on the client, some part of the database on the server. There may be many reasons to do that as well. Okay. Okay. So if you look at whatever I said, and then map that to how requests are flowing between the tiers. Okay, this is the picture you want to keep in mind. Okay, it's not unlike the picture I drew earlier. So your x-axis is time. Okay, the dark lines indicate that that component is executing. If it is dotted, that means that component is idle or blocked. Okay, so you start from the beginning. So the user is actually using the user interface. They might make a request. That request goes to the application logic. The application logic starts processing that request. Maybe it has to retrieve some data, so it sends a request to the data tier. The data tier could be a database. It processes that query, sends back a reply to the application logic. Application logic takes that response and then processes it. Maybe it constructs a proper reply, HTML page of some sort. Then it sends it back to the client. The client receives a response, continuous process. Okay, so that's your timeline chart of how requests and replies are flowing back and forth between tiers of the application. Right? So, as I said, common architecture, you can use this in all kinds of web application. There's a simple way of doing this called LAMP. I don't know if anyone has heard of LAMP applications. LAMP is an acronym, Linux, Apache, MySQL, PHP. Yeah. So it's basically, yes, your question.
Why do we need this architecture? Because it's definitely gonna take more time than the tier.
Okay, question is, why do we need this architecture? It's going to take more time than the two-tier architecture. What two-tier architecture are you referring to?
Sorry, like the previous one where
Okay, so
the client and the server.
So you still had three pieces. Okay? So there's a client server boundary, but there's still a application component, user interface component of the application component is a database component. This is just showing what code is at the client, what code is at the server. Regardless of what code is at the client and what code is at the server, your application user component is going to talk to the application server, is going to talk to the database. Okay? The only thing that will change is where the network boundary lies. This does not show where the network boundaries. It can be up there, it can be here, depending on where the components reside. Okay, so that's not a two-tier, it's just a client-server architecture. Always it was a three-tier architecture. Okay, yes, question.
Irrespective of the spectrum, whatever we've seen in the previous slide, this is what every spectrum follows, right? There's no way of overriding this.
So this is a time chart. Question is there any way of overriding this? This is just a time diagram of how requests flow and how processing is done. Okay, some of this is happening at the client, some of it is happening at the server, depending on which of these scenarios is true. Okay. Of course, if you have caches and whatnot, not all three tiers will be. So if, as I was mentioning earlier, you put a cache here, okay, that request might come, it may have a cache hit and then the reply will go. But if you don't, then this is your processing timeline. Yes, any questions? Okay. All right, so we'll now talk about some other architectures. The next one is essentially going from what is called a client-server architecture to client proxy server architecture. Okay, so we now introduce another entity which is called a proxy. Okay, so the proxy is essentially pretending to be a server to the client. Okay, so now there are two servers: there's an actual server and there's a proxy server, and then there is a client. Okay, now clients will, rather in the client server architectures, clients send their request to the server. In the client proxy server architectures, client sends their request to the proxy. The proxy can process that request, you will get a response. The proxy cannot process your request, it will send that request to the server. The server knows how to process that request, will send back a reply to the proxy will send a response back to the client. Okay, that's the basic idea. Now we'll say, why do we need a proxy? Why could, if the server is capable of processing the request, what did the proxy give us? What advantage is it giving us? Yes.
It's faster for some applications.
Sorry, can you repeat?
It's faster.
It is faster for some applications. Okay. Why is it fast? Can you elaborate?
Because let's say the service request is already in the proxy, then it can give us the result directly without visiting the client.
Okay. So what is being said is you could have proxy cache results. Okay. So if then you send it to the proxy, if the result is cached, you get. So web caching uses this architecture as well. There are two more hands. Yes.
It could be, the proxy could be geolocated closer to the user.
Okay. The server may be far from the user. You put another server that's closer to the user. Okay. And now your responses come back faster to you. Even if you don't have something cached, if you have to do full processing, the network hop to the proxy is slower than the network hop, or is faster rather, than the network hop to the server. So your responses come back faster. So it's faster. Yes.
Security, not exposure, internal system.
Yes, security, you may not have to do internal system. That's a tough one. There are different security trade-offs when you add a proxy. You can argue that your data is in multiple places. So whether it's more secure or less secure is up for debate. Okay. But yes.
Like the AWS has this blueprint deployment, does the proxy also work for that, that there's less downtime because whenever there's some update done to one server, the proxy still is running so that it reduces the downtime? Is that, does that is a valid example for this?
Yeah, so another point being made is the proxy could be storing results or content. You may make updates to the server may go down, but the proxy is still servicing requests, so it may reduce downtime. So that's an advantage actually. You can have proxies process requests even if the connection to the server is down. Sometimes that actually is an advantage. Okay, so in any case, we'll come back to this, but if there are more questions, please ask.
Can there be abstraction with proxy?
Can there be
We
what?
don't have to expose the internal details, but with the proxy.
What do you mean by detail?
We can get abstraction with it.
You can get an abstraction in that you can talk to the proxy, you don't have to talk to the server. That is true. Right, so the proxy can sometimes hide the presence of servers from. Okay, someone had a question there, yes.
Is it that the server is processing requests from lesser clients, so the response can be more personalized?
The question is can the proxy process and personalize requests? I'm not so sure about personalization, but certainly proxies can process requests to users that are closer to that proxy, geographically closer. So you can certainly get faster responses. Whether the responses are tailored, that's a different question because that will depend on how the application personalizes responses to clients. Okay. Somebody else had some question. Yes.
And could you explain the diagram once more?
Yes, I am coming to that.
Okay.
I haven't gotten to the diagram is very confusing, which is why I didn't want to come to it at the beginning. So that is a proxy server architecture. That's actually essentially a content distribution network. We'll come to content distribution network later, but just to explain what this is, the thing in the middle there, that's your server. Okay, here is an edge proxy, which is essentially referred to as an edge server. There's an edge proxy. There is another. So all these gray boxes, other than the one in the middle, they're all proxies. Okay. What this is showing is proxies can be deployed in different locations. In this case, a proxy is deployed in a company, in an enterprise network. In this other case, it says proxy is deployed in an ISP. Okay. And then there are clients that are accessing proxy. So this is how content distribution networks are built. And these are essentially caches in this case. Okay, they put a cache in an enterprise network. Okay, so for example, there are caches that content distribution networks are put in UMass. That's an enterprise network. Okay, that would be an example of this. Okay, there are caches also deployed in ISP. So if you get broadband from, let's say, Comcast or Xfinity, there are proxies actually sitting in there. So your home broadband request can also be serviced by proxies closer to it. Okay. So it's just showing that you can deploy proxies in multiple locations. It doesn't actually explain anything what I said, which is what are the benefits of proxies. But that is essentially an architecture of a CDN. Okay, yes, question.
Is there a reason why all of these connections are centralized to that one proxy server? Can they just go to each other, or do they have to all be centralized to that one house?
So question is, why is all this centralized? The centralized point is the actual server. It's not a proxy. Okay, so in one server, okay, many proxies, many end clients. That's a common example of how you scale the server. Okay, so a lot of streaming content actually is done this way. Okay, so you basically have the streaming content. Let's say it's a movie that's sitting on some server somewhere. Okay, but then you make copies of it in lots of different proxies. Okay, then users can just connect to their local proxy and you're streaming from there. So it reduces the load on the server because these proxies can essentially serve a much larger number of users than what the server could do. Okay, so it's not as much as a disadvantage. That's how actually you show that you can scale the ability of the server to process lots of users. Okay, yes.
For clarification, what's the difference between the edge servers and ISP? And what is an ISP? And why is there a coder on ISP and not on edge?
Question is, what is an edge server? What's an ISP? ISP is internet service provider. Okay. Comcast is an internet service provider. AT&T, Verizon are internet service provider, just that they do cellular internet, not wired internet. Okay? So essentially, content delivery networks are going to put caches wherever there are users. So one way to think about is these are business users, those are end consumers, right? So that's basically home users. These are enterprise users, but you put caches in enterprise networks, which are now wired typically, and the UMass LAN is wired, but that may not be wired. But that the reason there's a cloud is it's showing that it's a network service provider. That cloud means a network. Okay, yes, question.
Cache is the primary reason or primary benefit or use case that edge service systems are designed for, like, or is that the most use case? Caching, or is it any other use case where edge service systems are applied to correctly?
The question is caching the primary use case for edge servers or are there others? So caching was actually the initial use case for deploying proxies. Okay, that's no longer the case. We have something, we'll get to this topic later on, is called edge computing. So essentially you can deploy arbitrary applications at the edge that will essentially also have a component running on the main server. There's an edge component. So you can do arbitrary processing. So edge servers or proxies are evolved to a point where they're no longer dumb caches, but they are full-fledged servers that can run any application.
That's exactly what I'm saying. I'm unable to understand why the edge computing would be quicker or beneficial than the server.
Okay, so why is edge computing faster than going to the server? Very simply because the edge server is geographically and network-wise closer to end users than a remote server. Okay, this could be sitting in a cloud. Okay, that could be a cloud server. Cloud server maybe in California. Okay, you can put an edge server in a nearby town. Okay, maybe this is in New York or Boston. So it's easier to get to Boston than to California, right? So the network latency will be lower.
In reality, fundamentally, there's really no difference between the actual server and the edge server when it comes to computing, apart from in terms of computation purely, apart from it just being closer geographically. Is that
Okay. Question is there a difference between the edge server and the server that's sitting in the cloud? Often there is a difference because we will assume that the cloud has a lot more resources than the edge. Okay, these servers are not going to be as capable necessarily as that server. So they're although shown as one box, in the cloud you can put 10 servers, okay, or 100 servers if you want to. Okay. In the edge, these are smaller clusters, so you will often not have enough resources. So edge is going to be more resource constrained than the cloud, but the edge is also closer than the cloud. Okay, so there are many trade-offs. We'll get to that. Okay, but at the moment, you can just assume it's a cache. That's enough for today's lecture. Then we'll get to more complex cases.
In this diagram, the content actually travels from the server, like the main server, the cloud, and to the edge, and then from there, the client can actually access that. And the reason is like you have caching there, you know. But is it possible to have multiple proxies in the path of that? You know, not just like content to proxy and then to proxy.
So question is, can there be multiple entities between the proxy and the edge? That is called hierarchical caching. We'll get to that. Lecture 18 or 19. Not now. Okay. Right now, you just assume that there's either a server and a proxy, but you can have more than one proxies and you can essentially make a hierarchy. Yeah, that architecture also exists. Yes.
Can there be any disadvantage with this model because we don't get real-time data, right, from the server?
Can you explain the question again?
Can't there be any disadvantage with this model because we can't get real-time data, right?
Can you, so you're asking, is there a disadvantage of edge computing or proxies? Is that your question?
Because we don't get real-time data from the server.
Okay, you don't get real-time data for the server. So it depends on what you mean by real-time data. You're talking about caching, right? You cache some content. Okay. So long as the content is identical between the client and the server, it's still the right content. Now, if the content changes at the server, you have to implement something called consistency to ensure that proxies don't have old data. Okay. In that case, you might have outdated content, but that's a different problem. How do you ensure consistency? Now, if you're talking about a service, not a cache, right? You send a request, it processes that request, it gives you a response. That response is going to be similar to what the server provides. So in that case, there is not much difference other than maybe there's less resources. Sometimes there's also lower latency, which is an advantage. Yeah,
So it depends on the application where we can use this model, right?
of course, yes, it will very much depend on the application. You can't put it for every application. Okay. All right. So we have maybe 20 minutes for the last module, which is on decentralized architecture. So we are going to shift gear from client server. Everything we talked about are still client server. Okay. Now we are going to talk about a different architecture, which is called a peer-to-peer architecture. Okay. As the name peer suggests, we no longer have a distinction between what we call a client and a server. Okay, in the client server architecture, okay, implicitly we assume that the server is more powerful than the client. It can do more processing than the client. Okay, this is why client is sending a request to the server to process it rather than processing it locally. Yeah, because you have more resources there. In a peer-to-peer architecture, that distinction is gone. Okay, all nodes that are participating in your application, they are all equal. They're all peers of one another. Okay, now because they are peers, they can serve both as a client and a server. Okay, a peer can make a request to another peer. In that case, the first peer is a client, the second peer is acting as a server. But sometimes it can receive requests from other peers in the network, in which case it becomes a server for other clients. Okay, this is why it's called a peer. We don't have a distinction between a client and a server. You can be both a client and a server at the same time. You can be a client for some request you make, and you can be a server for requests you are receiving from other peers. Okay, that's our P2P or a peer-to-peer architecture. Now, there are many ways to build peer-to-peer systems. We are going to look at a couple. Okay, so what is shown here in this slide is essentially that shows you a ring, but this is called a structured peer-to-peer network. Okay, what by that we mean that the network, the peer-to-peer application has a structure. In this case, it has a ring structure. Okay, in another slide, you'll see some other structure and so. Now, what does this do? Okay, what does this indicate? This figure. So, this peer-to-peer architecture or system essentially is designed for retrieving content. Okay, early peer-to-peer systems were used for sharing music content. Okay, then they later on evolved to sharing all kinds of content. So let's assume that this collection of nodes stores some data items. What that data item is are not our concern. They could be music files, they could be images, they could be other documents. Okay, we don't really care. They're just pieces of data. Okay. So what we want is the ability for a user to come into the system and say, I want a content of this type. I want foo.java or foo.jpg. You specify some name of the content, and then this system should be able to figure out which of the nodes in the network stores that content and retrieve it. That's the goal. Okay. So when you send the request, you don't know who stores that content. You know it's there somewhere. You got to locate it and retrieve it. Okay. So how are you going to do this? And we are going to use a concept called a distributed hash table. Okay. So it's like any hash table. You essentially, what do hash tables do? There's a key and a value. You say where you specify a key, it gives you a value. Okay. So we'll assume that there's a distributed hash table which has file names. Okay. And there is a location saying this file is stored on this node, this file is stored on this node. So you have a big table. Okay. Now we don't want to keep this, and this is a hash table. So we don't want to keep this table on one node because then you won't be able to scale. So we are going to distribute that hash table. That's why it's called a distributed hash table. So each node in your system is going to be responsible for serving requests for some number of entries in that hash table. Okay. It will additionally store some content as well, but at this point we are not talking about content. We're just talking about the hash table itself. Okay. So that is essentially what this structure is going to show. Okay. So we will assume that nodes in your network, peers in your network are arranged in a ring topology. Okay. So we will assume that they are numbered 1 through n. Okay. All the entries in the ring. And when a node, a peer essentially becomes part of that network, it has to pick an identifier for it. So here is, so all the dark nodes are actual nodes. So here is node 7. Okay. Here's node 4, here's node 1, and so on. Okay. We will also assume that all the items are not actual names, but they're just numbered items. So you number all the data items 1 through n. Okay. Nodes also have IDs that may go from 1 through n, but there aren't n nodes. There are more items than nodes. Okay. So now, what does this do? Okay, if you pick an ID for yourself, which is in this case 7, you are responsible for serving all requests for items from the previous node to you. So say 567 is your responsibility. Okay. Data items 567 is responsibility of 7. Here's node 12. Okay. So there's no other node between 7 and 12. So that node is going to essentially be responsible for items 8 through 12 and so on. Okay. So essentially what we have done is each node Okay, it's essentially serving some subset of the hash table. Okay, the idea of that node determines which entries of that hash table is its responsibility. Okay, so if you essentially say the hash table has 100 entries, you are, let's say, node 5, then you do items 1 through 5. And there's another node that picks 10, then it has to do 6 to 10 and so on and so forth. So based on your ID, you essentially get responsibility for serving some number of items in your hash table. Okay, so essentially that's how you're going to distribute the hash table responsibilities across nodes. Okay, now there is another dimension here, which I'm not going to talk about, saying I essentially say, where is item number 30? Okay. Now these nodes have to cooperate to track down 30. Okay, because there's no centralized table. The table is distributed. The table was in one place, you would just look up that entry, you're done. But you don't know where to send this because you don't know what nodes are in the system, what IDs they have, and so on. Okay, so you are going to inject your query into some node, and that node is going to keep forwarding that query until it hits the right node that has item number 30. And the response is going to come back from there. This is called query routing. Okay, I'm not going to get into query routing in this case, but it's something you should know has to be done for you to look up the hash table. All I said is how our hash table divided. Okay, that's divided in a random fashion because nodes randomly pick an identifier for themselves and they join the ring. The ring is essentially all the entries, and then you are essentially going to be responsible for all the entries from the previous node to yourself in that hash table. Is this clear? Question.
Yeah, so node 12 looks like as responsible for 5 requests. And let's say that was too much for node 12, node 12 goes offline. Would node 15 then be responsible for like kind of picking up 12's load, and then if that was too much for 12, maybe
Yep.
the load's not too much for 15, and you ever get like a kind of a wave going around that just overloads all the nodes and
Okay. Question is, node 12 has responsibility for 5 data items, 8 through 12. What happens if node 12 goes offline? Okay, so peer-to-peer networks are designed to handle node failures, node arrivals, node departure. So there's essentially this notion of churn where peers, because they are not servers, they're assumed to be less reliable than servers. They fail more often, they disappear, as opposed to a server that might be more reliable than clients. The peers are like clients, so they can just disappear from the network. So you don't want your system to fail because some client just disappeared saying I'm no longer a peer in this network. So what the system will do is whenever a client departs as a peer, all of its responsibility gets reassigned. Okay? So in this case, if 12 is going to go away, 15 has to take over 12's task because it is now responsible for everything from 7 through 15. Okay? Now maybe it has a high load, but that's the way it is. Okay? Maybe some other node joins later and then it will take on some tasks of node, whatever that node was doing. Okay? So things like that are going to happen in this network. Yes.
So you mentioned earlier an example that let's say somebody is searching for a 30 node, so they have to communicate with each other and find that. So is the communication going on only between the actual nodes, that is 1, 4, 7, 12, and 15, because the rest of them are just a subset of the actual nodes. So nobody directly talks to these subsets, right? They talk to the actual nodes.
Yeah, so anything that is a dark is an actual machine. Anything that circle is just a data item that is stored on that machine. Okay. So in this case, the actual nodes or machines in the network or peers are 1, 4, 7, 12, and 15. Okay. There are just 5 of them. Okay. They have to essentially handle all the queries for all the data items. There are 16 data items here, 0 to 15, and there are only 5 nodes that are handling all of that data item. Okay. So what will happen is when you insert a query, the simplest way to route queries and send a query says 13, 7 says that's a higher ID than me, I'll send it to the next node, so I'll send it to his neighbor. We'll go to 12, 12 say, okay, I can't do 13, I'm going to send it to the next node. You go to 15, 15 will say, yes, I know where 13 is and send back a reply. Okay? Now that's linear search. That's not how you're actually going to do it. Okay, but you're going to do something smarter than that. So it's actually a log n, but that's a trivial way of understanding how you're going to search. Okay,
So
yes.
1, 4, 7, 12, and 15 are the actual peers we are talking about.
Yes, 1, 4, 7, 12, 15 are the peers. Anything in dark and gray is peers. Okay, everything that's dotted are just data items stored at the next peer. Okay, yes, question.
How is if a new concept, how is the assignment done? Is it random or depends upon the storage?
Question is how when a new peer arrives, how is it going to be assigned? Okay, the peer picks a random ID that's not yet chosen, and that's where it joins the net. Okay, so it might be that there are more nodes on the first half than the other half, but assume it's a uniform distribution. So over time, probabilistically, you will be balanced. Okay, but there's no guarantee. It's all probabilistic. Yes.
I've joined the network more recently and I have unique content which the network doesn't have. So once I disappear from the network, does it mean that everyone in the network wouldn't be able to see that content, or is it like my content would be shared among other peers as well?
The question is, if you're a peer in the network and you have some piece of content and the peer disappears, what happens to that? How is it? So typically, if you want to ensure the content remains available, it has to be stored at more than one peer. Because if the peer goes away and that's the only piece of only copy of that file, and the file is no longer available, you might still have some hash table that says go to this node, node is gone. There's no such node anymore. Right? So you would typically replicate in this scenario to avoid that from happening. Okay? But if you don't replicate exactly what you said is true, the content becomes unavailable. Okay? Yes, there was one more question there.
So if you replicate, there has to be some sort of central mechanism which will decide this data goes into what or node.
Okay. Question is, if you replicate, is there some central mechanism to decide what goes in what node? There's no central entity here. That's peer-to-peer nodes. That's why it's called decentralized, right? So it's all done. You can use randomized algorithm. That's a simple way. You just toss a coin, pick two nodes. And those are the nodes that will have it. Or pick three nodes at random and say, this here, take this content, replicate it. Right?
How will it know which node to get that data?
Yeah, so that's a different question. If you this doesn't show any replication, I'm just saying you might have to replicate for reliability. This is just showing one copy of each data item. Right? Okay. In this case, assume there's only one copy, and the hash table just tells you. You go to 13 and you say, where is 13? Say it's at node number 15. Okay. Or node number 15, at least knows where 13 is stored, if it's not stored there locally, because the value of that, when you do a key value lookup, the value says it's stored at machine with this IP address. Right? Okay. So peer-to-peer networks were very popular for storing music content. Okay, none of them are around anymore, or very few of them are around. But some of the ideas that came out of it are still prevalent. Right? One of those ideas is a distributed hash table. Okay, that has outlived the notion of a peer-to-peer network. DHTs are used in variety of distributed systems. I just put some examples here. They're used in distributed key value stores. That inherently is a DHT. They're used in Memcached, which is used as a caching system, very popular one for web application, used in Apache Cassandra and so on and so on. Okay? Another concept that came out of this was consistent hashing. Okay? The consistent hashing is a theoretical concept. Probably if you take 611, you might actually learn it there. What it says is when peers come and go, how do you rebalance the distributed hash table so that peers have an equal number of entries they store? Otherwise, some peers might have more entries, some have less. Okay? And you want to do this without rebalancing the entire DHT. You can't say there are 100 items, there are 4 nodes, everybody gets 25 and everything moves around. So you want to rebalance the DHT by making minimum number of changes to the hash table and yet have balance. Right? That concept is called consistent hashing. Right? And that also is related to distributed hash table. Again, that's a theoretical concept. We are not going to study consistent hashing here, but it's something you should know. So when your DHT is a good property to have is essentially consistent hashing, which ensures that the hash table is equally distributed in spite of churn. Okay, that's not equal, but reasonably balanced despite churn. Okay. Next concept is essentially a different type of peer-to-peer system. It's called content addressable network, or CAN. Think of this as a two-dimensional key value store. Okay. Every item has 2 keys. Okay, key K1 and K2, and then it gives you a value. Okay, so you can say, I want file foo. That's the first key. And you say the type of the file is a JPEG image. It's a video. It's a Java file. Okay, that's your second key. Okay, so you say, I want foo, it's a Java file, and then you say, here is where it is stored. Okay, so there are two dimensions to your keys, and there is essentially an entry. So you can think of this now, instead of a ring, conceptually, it now looks like a grid. Okay, so there is a x-axis key and a y-axis key. So every point in that coordinate space is a potential data item, and the coordinates of the data items are the two keys. Okay, here is just shown as numbers. The keys could be anything, but these could be, here is shown as a number from 0 to 1 on the x and the y-axis, but you can think of them as strings of some sort, okay, that you can map into a numeric space. So each point in that grid essentially is a data item. Now, the same concept is true as we said before. There are nodes that are responsible for serving requests for those data items. Okay, so the points here that are shown are actual nodes. Okay, so nodes pick a random coordinate and they join the network, and they essentially get a rectangle that says you're responsible for all data items that have coordinates within that rectangle. Okay. So here is a node which is 0.2, 0.3. It's in that rectangle. So all data items that fall in that rectangle that are coordinates there are essentially going to be its responsibility. Okay. If a new node joins, okay, you'll see that there's a new node has joined there. Essentially, you will basically split that rectangle into two, and then each node then takes over some responsibility. And a node leaves, then you essentially take all of its responsibilities and then you split them or merge them with some other nodes. Okay, not unlike what you did in CORD, but now it's two-dimensional, so things look a little different, but they are essentially doing the same thing. Right? You have coordinate space. Each item has a coordinate, which is its key. In this case, there are two keys, not one. And then nodes take responsibility for serving some part of that address space. That clear? Yes.
Earlier in the distributed decentralized architecture, I was able to relate the data points and this list of data that the machine is corresponding with. But when we come to dimensions and coordinates, I'm not able to relate how we're going to match certain data to a certain machine.
Yeah. So you don't have to think numbers, think strings. Can understand strings, right? So assume that strings represent file names. Okay. And there's a file type is the second dimension. So there are file names and file types. Okay. File types could be, there's a Java file, there's a JPEG file, there's a movie file, and file names are all strings of files that are stored in the network. Okay. So that's your X and Y coordinate. So you have one node that says you serve all Java files starting from A to C. Another one will say you store or you are so responsible for Java files from this string to this string. That's how you're dividing it. Now you can take any string and essentially hash it and you'll get a number. Right? You can just hash a string, you'll get a number. That's your numeric ID. Right? So you can represent your strings, file names, and numeric ID. So now you have coordinates which are just numbers, but they're actually strings or types or any type of key, doesn't really matter. Okay, so that's essentially what we have done. We have taken responsibilities of each node and we have mapped it into a coordinate space. Okay. This question.
So in that example, the example you just mentioned, each user would have their own network.
Question is each user would have their own network. So the network is a peer-to-peer network. Each user may have a machine that can act as a peer.
Well, my concern was like if you have multiple files with the same name, it seems that they would collide.
Question is what happens if you have multiple files with the same name? Yeah. You can share a photo with some foo.jpg, somebody else can share a photo with foo.jpg with two pieces of content with that name. You can't prevent that from happening. You essentially will have maybe two entries that are written saying there are two of these. Whether they're the same or not is up to the user to figure out. Right? I mean, if you think about when music files were shared, many people shared the same song. And so there are 10 copies of it, but they may not be identical copies. You could have shared your version, somebody else shared a different version with different bitrate, higher quality. So there are multiple copies floating around. That can happen. We don't worry about it. You can just assume that you will have multiple. It's just like replicas, and you could have 10 copies of something, and you'll get saying, okay, the hash table will say there are 10 versions of this in my network. You'll get all of those responses. Any other questions? Yes.
Advantages of this for the period decentralized.
Okay, that was my question. Are there any differences or advantages of doing things in 2 dimensions versus 1 dimension? What do you get by having 2 keys versus 1 key?
So the replicas of name could be like done here, but not in the previous.
Replicas can be done here. Actually, you can have replicas there too. There's no difference. In fact, you might have replication in both. Okay? Now, technically, there's no difference because if you think about the 2 keys, you say it's file name and file type. Okay? You can just take those strings and append them. You got 1 key. And you essentially are going to go back from 2 dimensions to 1 dimension. So from a conceptual standpoint, this is no more powerful than the previous case. But there's sometimes you query on multiple attributes. So this gives you a little more expressive power than, shouldn't say more expressive power. This allows you to formulate queries in a way that may be more easier to understand. Okay, but in terms of technical details, they will not give you anything more than the other. Okay, yes, question.
The lookup might change, right? Suppose you have all PDF files or JPEG files separately. So if I query it, so you just go to that JPEG and find it. But in the previous case, it has to go through all the files. So
Question previous case, you have to go through all the files. Here you can do JPEG file. At the end of the day, they are going to be numbers. Right? So you're querying a specific thing which says, do you want foo that's a PDF or do you want foo that's a JPEG? If you say foo.pdf, will get you a PDF. Well, it will at least get you a file with the name foo.pdf, whether it's a PDF or not, a different matter, right? So it's not going to be very different in terms of expressive power. It's same. Just 2 different ways to do the same thing. Okay. I will end by saying that even though this concept is also not used as a peer-to-peer network, the main concept that came out of this was essentially this notion of content addressable network, which is that all content in my network has an address. So rather than using things like TCP/IP and HTTP, you just specify the name of the content and the network will get it for you. Okay? So essentially, it's not unlike what we're talking about RESTful services, but that has led to this whole area called information-centric network. There is a different way of building networks. Networks can be thought of a collection of content. Content have names. I just specify the name and I get that content. Okay? Similar to how you had RESTful APIs that allowed you to have names for content, the same kind of stuff. So that is still an active area, even though I would not think that CAN as a peer-to-peer system is actually being used, but content addressable networks, area of research, people are deploying this. Okay. So we ran out of time. So let's stop here. I'll finish the remaining slides next time.